Hello everyone, welcome back to STR8CHEM. In this video, we're going to talk about solubility products, molar solubility, and solubility of salts. We need to know that most salts are slightly soluble or insoluble in water. In this discussion, we're going to focus on the slightly soluble salts. What does it mean by slightly soluble salts? Basically, slightly soluble salts will be able to form a saturated solution at room temperature. Now, the question is, what does it mean by saturated solution? So, saturated solution is when the solution will be able to form a dynamic equilibrium. Okay, so in a saturated solution, a dynamic equilibrium is established between the dissolved solutes in the solution in the form of ionic and the undissolved solutes of the salts in the form of solids. Thus, we can imagine that in this discussion, we're going to be dealing with reactions that use the reversible arrow because the saturated solution of slightly soluble salts will have dynamic equilibrium. So you can recall the chemical equilibrium and also the other ionic equilibria topics that we have discussed before we have reached to this point. And yes, for the saturated solution, we're going to be dealing with something that will exist at equilibrium. Some slightly soluble salts, these are just the 3 examples over here. We have a lot more examples. So since the slightly soluble salts will be able to form saturated solution, and the saturated solution can form a dynamic equilibrium, the equation for slightly soluble salts will be written as follows. For example, for AgCl solids, this solids right here will be able to exist at equilibrium with its ionic species when it is dissolved in water. Same goes to calcium sulfates. Same goes to barium fluoride. Let's imagine the saturated solution can be drawn like this. If you have a salt, let's say AgCl solid, in a form of solids in the beginning, and then you try to dissolve that in water. So when the solution reaches saturatedness, you will be able to imagine that in your beaker now, you will be able to see solids, AgCl, inside the beaker exist together with the aqueous species of the AgCl, Ag plus aqueous and Cl minus aqueous, as what we have drawn over here. So this is what we meant by saturatedness. So what we have right here is actually a saturated solution. Okay? So you have your solid, you will be able to see it, and then in the same time, in the aqueous phase, we have the ionic species of the salts exists at equilibrium. Now, since a saturated solution has equilibrium, we can have the Ksp of the reaction. Okay? So this is what we call as the solubility products. Ksp. S right here stands for solubility. P of right there stands for products. And K is the equilibrium constant. Now, if you recall, the equilibrium constants that we have learned in the past before we reach this point of the semester, to write K is simply the products over the reactants, okay? The concentration of product to the power of a certain number over the concentration of the reactants over a certain number. So it's the same way of writing KSP. So how to write KSP for, let's say, AgCl solids with its ionic species, CaSO4 solids with its ionic species, and BaF2 solid with its ionic species. How do we write that? Remember, when we have solids involved, these AgCl solids, CaSO4 solids, BaF2 solids will not going to be part of the KSP because they are pure solids and they are constant. So how do we write the KSP for all of these reactions right here? It's very simple. So for AgCl, the way we're going to write it, so we're just going to write KSP equals to concentration of the Ag plus to the power of 1, because you have 1 mole right over here, and concentration of the Cl minus to the power of 1, because you have 1 mole over here. So this is how you're going to write the KSP expression for AgCl solids that exist at equilibrium with its ionic species. Number 2 and number 3. So it's just the same process, KSP, concentration of Ca2 plus times concentration of SO4 2 minus. Okay, so 1 mole, 1 mole, 1 mole, 1 mole to the power of 1 to the power of 1. So what about barium fluoride right here? So the KSP for this is written like this. Concentration of Ba2 plus, okay, 1 mole right here to the power of 1, times with the concentration of F minus to the power of, now you have to the power of 2. Why? Because you have 2 moles right there. As you can see, the way we're going to write KSP is exactly the same as how we're going to write the KC, KP, KA, and KB. So it's quite simple. Now, there are 2 ways to express a salt solubility. Number 1, through molar solubility. Number 2, through solubility. Molar solubility is defined as the number of moles, okay? So it is the number of moles of the solutes in 1 liter of the saturated solution. Therefore, the units will be written like this, mole per liter. Whereas for the solubility, the number of grams of solutes, okay, solutes is the salts, number of grams in 1 liter of the saturated solution. So this is how you're going to write the units, gram per liter. That is the difference between solubility and molar solubility. You have the word molar over here, therefore mole per liter. For solubility, it will be in terms of grams per liter.